All right, hello everyone. Hope you're all doing good. So today we're going to be learning about the operations of rational expressions. We're going to do four basic operations, but before we move on, let's make sure you know exactly what a rational expression is. So as you can see here on the slide, a rational expression is kind of a ratio between two different polynomials. So if either the numerator or the denominator is a polynomial, then it's considered a rational expression. And we're going to be doing addition, subtraction, multiplication, and division today. So knowing how to simplify rational expressions is going to be crucial to actually doing these operations because having them down to their simplified forms, it's going to make the process that much easier. So this is a very important concept to know. So how do you actually simplify? So let's start with this example. You actually you factor out all the numerators and then the denominators, and then you cancel out the common factors. So for this example, you have 4x cubed minus 6x squared over 2x. So all of them have 2 in common, and the numerator actually has x squared in common. So you can bring out that x squared as well as the 2, and you can factor out the 2x squared, and you get 2x minus 3 times 2x squared. And then on the bottom, you have nothing to factor out. You can cancel out the 2's because it's a common factor, and then you can cancel out the x as well. So that leaves you with x times 2x minus 3. And then this is another example. 2x plus 4 over x squared plus 5x plus 6. And on the top, you can factor out the 2, so you get 2 times x plus 2. And then on the bottom, you can actually use the sum product pattern, and you get the x plus 3 times x plus 2, which is the same as x squared plus 5x plus 6. So here you can cancel out the common factor, which is x plus 2, and then you're left with 2 over x plus 3. So knowing how to do this kind of factoring, it's going to be essential in solving all of the operations problems. So we're actually going to start with multiplication and division because it's a lot easier to understand and they have less special cases. So just as you can multiply and divide fractions, you can actually multiply and divide rational expressions. In fact, you use the same process for multiplying and dividing these expressions as you use for multiplying regular fractions. So we're going to focus on multiplication this time. And remember, there's two different ways that you can multiply fractions. So here we can either start with multiplication and then factor, or we can factor and then multiply. So here we're going to start with the first method. We're going to multiply. So you get 36 over 40 because 4 times 9 is 36, 5 times 8 is 40. And then you do some prime factorization and you get 3 times 3 times 2 times 2. And on the bottom, you get 5 times 2 times 2 times 2. Now you can cancel out all the 2's here. And then you're going to be left with 3 times 3 over 5 times 2. And then all of the 2's just become a 1. So then the simplified version of the answer would just be 910. So here, the first method is multiplying and then factoring. And then you can also do the opposite. You can actually factor before you multiply. So here, you can see that they actually did 2 times 2, and then divided it by 5. And then for 9, it's 3 times 3. And then for 8, it's 2 times 2 times 2. And it's essentially the same process, but they just did it before rather than after. So once you cancel out all the common factors, you get 1, and then it's 3 times 3 over 5 times 2, 9, 10. So you have to realize that both of these methods, they have the same product. So you have to decide which one you're going to do. So in some cases, it's going to be easier to multiply and then simplify. But in others, it's going to make more sense to simplify the fractions before actually multiplying. So let's go ahead and do some examples of actually multiplying these expressions.
All right, so here we have example number 1, and it's asking us to find the product in the simplest form. We have 5a squared over 14 times 7 over 10a cubed. So before we get right onto the problem, I want you guys to know these exponent rules really well because we're going to use a lot of this when multiplying and dividing rational expressions. So for the first rule, it's x to the a times x to the b is going to be the same thing as saying x to the a plus b. So if you have x squared times x cubed, that's the same thing as x to the fifth power. Now, for division, you have x to the a divided by x to the b. That's the same thing as saying x to the a minus b. So if you have x to the power of 5 divided by x squared, that's going to be the same thing as x cubed. So we're going to have to use these rules in solving for the product or quotient of these rational expressions. And it's really important to note that these rules only apply if these are the same basis. So if they're both x or if they're both y, that's the only time you can apply this rule. So for this example, I'm going to multiply and then factor, but for the next example, I'll do factoring first and then multiply. So let's get right to it. So the first thing we're going to do is multiply on the numerator and the denominator. So we have 35, because 7 times 5 is 35, right? So you have 35a squared, and the a squared doesn't change, it's still a squared. And then on the bottom, you're going to have 140, because 14 times 10, right, is 140 times a cubed. All right, so now let's go ahead and factor. So let's list all the prime factors of 35 squared. Okay, and then we can actually, instead of doing a squared, we can actually separate the a squared as well. This is the same thing, right? A times a is the same thing as a squared. So let's do that here as well. So 2 times 5 times 2 times 7 is going to be 140, and same thing with the a. Okay. So there we go. We got all the prime numbers of these two values, so 35 and 140. And now we can start canceling all of the common factors. So we notice that there's a 7 there, right? So we can cancel out that 7. Okay, and then there's also a 5 here. So we can cancel out that 5. And if you look, there's also 2 a's here, and then there's 3 a's down here. So we can just cancel out those 2 a's and cancel out those 2 a's down here as well. So that leaves us with 1 over 2 times 2 times a, which is just 1 over 4a. And that would be the product in the simplest form for this rational expression. So it's as simple as that. It's literally just multiplying like fractions, and you'd have to, so for this example, we actually didn't have to use these exponent rules, but if you wanted to, this is how you would have done it. So instead of separating them into separate a and a, you just have a squared over a cubed, right? Instead of separating them, you would get a 2 minus 3, okay? Which is just a to the negative 1. And any variable to the negative 1 is just 1 over a to the 1, which is just 1 over a. And it would be the same, right? Because you would have 1 over 4 times 1 over a, which is the same thing as 1 over 4a. So you could do it this way, but beware, like, be careful of doing it this way, because especially if you go into higher powers, if you go into a to the 5th or a to the 7, it's going to be really exhausting writing every single a out. So it's really important to know these rules, and you can just apply them like this, and it'll make your life a lot easier. So, but anyway, so that's how you do it using the first method and using these exponent rules. So we're gonna move on to the next example now. All right, so here's example number 2, and you're gonna notice right away there's a lot different about this example. So some rational expressions, they actually can contain quadratic expressions or other multi-term polynomials. So to multiply these kinds of rational expressions, the best approach is to first factor them and then multiply. Because if you do go ahead and multiply first, it's going to get really messy, and You can find the same product. The answer will be the same, but it's gonna take a lot more time. So that's why it's a lot more the process is a lot more smoother if you go ahead and factor out first. So that's exactly what we're gonna do. So for this first expression, we're gonna do it's a squared plus 4a plus 4. So if you use the sum product difference, you're gonna recognize that it's the same thing as a plus 2 times a plus 2, right? Because 2 2a plus 2a is 4a, and a times a is a squared, and then 2 times 2 is 4. So that's all good. All right. And then you have 2a squared minus a minus 10. So for this, you'd have to do 2a minus 5, a minus 5 times a plus 2. And let's make sure it's right. 2a times a is 2a squared. That's correct. 2 times 2a, which is 4a, minus 5a, which is minus a. And then minus 5 times 2 is minus 10. Okay? So that's all factored out and ready to go. Let's do the same thing with this. So a plus 5. We can't really factor that out anymore. So let's just leave it as a plus 5. We can, however, factor out a from both of these terms. So you get a plus 2. All right, now we go ahead and cancel all the common factors, just like we did last time. So we cancel out the a plus 2, and then we cancel out this a plus 2 as well. Okay? And then you're left with a plus 5, 2a minus 5 times a. And I mean, at this point, that's all we had to do, right? So this became 1. So we just multiplied 1 times a plus 5, and that's what we got. And then here we multiplied 2a minus 5 times a, and that's what we got here. So the final answer would just be a plus 5 times a 2a minus 5. There you go. So that would be the final answer. So whenever you see these kinds of questions, it's always better to factor first and then multiply, because it'll make your life a lot easier. Because if you had to multiply these two, then you would have to do foiling, and that would be a cubed, and you would get 5a squared and all that stuff. You don't really have to mess with all of that. So if you go ahead and just factor first, it'll make your process a lot more easier. And you might have noticed these as well. This is just, the problem gave us these. It said that a cannot be equal to -2, 0, or 5/2. This is because we can't have 0 as our denominator, right? So if we were to do it, factor out here, we notice that it's -2. If we put in a -2 here, that's just going to make it 0, and that's going to make the entire denominator 0, which is going to be undefined. So these are just values of a that make this the product of this rational expression undefined. But yeah, the final answer would be a plus 5 over a times 2a minus 5. So these are the two main methods that you're going to use to multiply fractions, and you get to decide which ones to do, but usually you can tell by the way the problem is formatted which one to use right away.
Now moving on to division of rational expressions. So this is also the same process as dividing regular fractions, but specifically for rational, or just in fractions, you notice that you have to multiply it by the reciprocal, and the reciprocal just means that you're flipping the numerator and the denominator. So 4/3 is just going to become 3/4. 3/4 is the reciprocal of 4/3. So once you find that reciprocal, though, it's the same thing as multiplication, because once you do the reciprocal, you're just multiplying again. So for specifically rational expressions, you're going to keep the first rational expression the same, change the division sign to a multiplication, and then take the reciprocal of the second rational expression and then use the same rules that we just applied for multiplication, use those same rules for solving these. So let's go ahead and do an example of dividing rational expressions.
Alright, so now we have an example of a division problem. And like I said before, it's simply doing the reciprocal and then multiplying. So here we have find the quotient in the simplest form. We have 3x squared over x plus 2 divided by 6x to the fourth divided by x squared plus 5x plus 6. So the first thing you do, as soon as you see this division sign, the first thing you're going to want to do is flip these two, the numerator and the denominator, because that's what reciprocal means, right? So you're going to have 3x squared x plus 2 divided by x squared plus 5x plus 6 divided by 6x 4. So as soon as you see that division sign, keep the first rational expression the same, and then flip the other rational expression. So you get x squared plus 5x plus 6 over 6 to the fourth. Now it's just a normal multiplication like we did in the other two examples. So this, I'm going to use the factor first and then multiply method for, and because, well, you can see both of these are quadratic expressions, right? And I'm not trying to do a lot more work than I need to. So I'm just going to factor first and go that route. So for this one, for this expression, there isn't that much to factor out, so I'm just going to leave it as it is. Okay. But there is, I can factor this out. So let me do that right now. X plus 2 and x plus 3. 6x4. I can't factor anything out from there. Okay, so now I can cancel out the common factors. X plus 2, x plus 2, right? And that leaves me with 3x squared, x plus 3 divided by 6x4. Okay, you might have noticed that 3 and 6 can also be factored out. So I can take out the 3 and have it like this, right? And then same thing with the 6. Take those out. That becomes a 1, and that becomes a 2. So then you have x squared times x plus 3 over 2x4. And if you remember the quotient rules back, exponent rules, my bad, exponent rules back when I showed you guys, if we have the same base, we can just, it's the same thing as x2 minus 4, right? So that's exactly what we're going to do. So we're going to cancel the x squared on top and make this 2, because 2 minus 4 is the same thing as x to the negative 2, right? Which is the same thing as 1 over x squared. Exactly what we have. So we're going to be making that 1 over x squared. So now we just have x plus 3 over 2x squared. Okay. And then, so your final answer in your simplest form would be x plus 3 over 2x squared. So there you go. So division between rational expressions is essentially the same thing. So that the most important aspect that you have to remember is that just multiply it by the reciprocal. So just flip this and then just follow the normal multiplication method. So that's just the main thing. And yeah, and that's it for division. So we're going to move on to addition and subtraction next.
Okay, now we finally moved on to addition and subtracting of subtracting rational expressions. So this is actually the last aspect that we're going to learn, because there's 4 different scenarios, and it's different for each type. And I'll go over each type with an example so you can understand how to solve each one. So the 4 major scenarios are like denominators. So you're going to have to know how to add and subtract rational expressions with like denominators. You're going to learn how to add and subtract rational expressions with unlike denominators using a greatest common denominator. I'll explain what that means. And then you're also going to add and subtract uh, expressions that don't share any common factors. And finally, you're going to do some adding and subtracting of more than two rational expressions. So we'll start with like denominators first. So for like denominators, adding rational expressions with the same denominator, it's like the simplest place to start. So let's just it's the same process as adding two fractions that have the same denominator. So 2/9 plus 4/9, they have the same denominator. So you just do 2 plus 4 is 6, and then you can simplify that down to 2/3. Same thing for subtracting. It's the same denominator, so it's just 3 minus 1 is 2. 2 over 14, and simplify down to 1 over 7. So to add for rational expressions with like denominators, it's essentially the same process, and I'll show you with some examples.
All right, so here's two examples of doing it with like denominators. So let's start with an adding example. So we have, as you can see, it's the same denominator. So we're going to simply just add the numerator, just how we did with normal fractions. So it's going to be 2x squared plus 8x squared plus 2. And since it's the same denominator, we can just put everything over that single denominator. And since it's asking for the simplest form, we add these like terms, right? Because they're both x squared. 2x squared plus 8x squared is 10. X squared plus 2 divided by x plus 4. And if there was, we can factor out the 2 if you'd like. It's not necessary because it doesn't get canceled at the bottom, but you can factor it out if you want. Either one of these answers is fine. But if there was like a 2x plus 8, then you could cancel out the 2's, but in this example, it's not necessary. But yeah, that's the same. That's the thing. That's how you add. And now let's do a subtracting example. And again, making sure that they're both like terms, right? So 4x plus 7 minus 2x minus 8. Okay, so here you got to recognize that when you're multiplying a negative with this numerator, you're going to multiply both the 2x and the plus 8. So that's going to become negative, negative 2x, and then that's going to also become negative. So you have 4x plus 7 minus 2x minus 8 over, again, same thing as adding, x plus 6. Now, you get 2x minus 1 over x plus 6. Okay, so, and we can't really simplify it anymore. That would just be our final answer. So yeah, it's pretty simple. This scenario anyway, in this case, if they're just the same denominator, then you can simply just add them like how you'd add a normal fraction, and you can simply subtract them how you would subtract a normal fraction. So let's move on to the next scenario.
Okay, for unlike denominators, before adding and subtracting rational expressions with unlike denominators, you're going to have to find a common denominator. Once again, this process is similar to the one we used for adding and subtracting numeric fractions with unlike denominators. And in order to solve this, we're going to have to find the least common denominator of 6, 10, and 4. So for this example, we're going to have to find the LCM of 6, 10, and 4. So let's do some prime factorization. So for 6, it's 3 times 2, 10, 5 times 2, 4, 2 times 2, and then the least common multiple turns out to be 3 times 5 times 2 times 2, which is 60. So now that you've found the least common multiple, you can use that number as the least common denominator for all of these fractions. And you're going to have to multiply each of these fractions, so 5, 6, by some number to get whatever the LCM is. So in this case, it was 60, right? So in order to get from 6 to 60, you'd had to multiply by 10. So you can't just multiply the denominator by 10. You'd have to do both the top and the bottom, so both the numerator and the denominator. So you multiply by 10 there. Here it's 10 to 60, so you multiply by 6, top and bottom. Here it's 4 to 60, so you multiply by 15 and 15. And now you notice that it's the same, right? It's just all of them have the same denominator, and it's exactly what we did last slide. So you just add up all of them and you get 143 divided by 60. So now let's apply it to some rational expressions with some examples.
Okay, so now we're going to deal with unlike denominators. And let's just jump straight into it because we're going to have to do a lot. So first of all, notice that it's unlike denominators, right? And now we're going to have to find the prime factorization of both of these denominators, just like we did with normal fractions. So 15m squared, the prime factorization would be 3 times 5 times m times m, okay? And then for 21m, it would just be 3 times 7 times m, sorry. And now the least common multiple in this for these two denominators would then be 3 times 5 times 7 times m times m. Okay? And you guys, I'm going to assume that you guys know how to find the least common multiple, but that's what it would be for these two denominators, and then you would get 105m squared. So our goal is to make both of these two denominators equal 105 m squared. So we're going to rewrite them right now. So for 15m squared, how do we get that to go to 105m squared? Well, we just have to multiply it by 7, right? Because 15 times 7 is 105. So you could have done that on your calculator or just in your head. 105 divided by 15, you multiply by 7. What about 21m though? You're gonna have to multiply that by m to get 105m squared, but also you're gonna have to multiply that by 5. So you have to multiply a total by 5m to get 105m squared. Okay? And then now, so you can't simply multiply the denominator by 7 or simply multiply the denominator by 5m. Whatever you do to the denominator, you're going to have to do to the numerator as well. So that's exactly what we're going to do here. So we get 2n divided by 15m squared. So we said we're going to multiply by 7 to get 105m squared, right? So let's just do that right now. 2, 7. And that gives you 14n, okay, divided by 105m squared. And then the same thing, 3n over 21m, okay, and we said we're going to multiply it by 5m. So 5m on the top and on the bottom to get 15mn divided by 105m squared. Okay, now we can use what we've learned from the previous scenarios. Since these are both like fractions, they both have like denominators, we can simply add them like normal fractions. So it's just 14n 105m squared plus 15mn divided by 105m squared, and just add them like normal fractions. So 14n plus 15mn divided by 105m squared. And normally you can just leave it like this, but here you notice that you can actually factor out the n, right? So we get 14 plus 15m divided by 105m squared. And if it was asking for the simplest form, this would be it. So the main aspect of this scenario is figuring out what the least common multiple is and then making that your denominator, and making sure to multiply the numerator as well by whatever value you have to multiply it by. So just the least common multiple and making sure you multiply to the numerator and then denominator, and then it's a simple like fraction, like denominator, sorry, addition. So yeah.
All right. So now we have adding and subtracting rational expressions that don't have any common factors. So far, all of the rational expressions we've added and subtracted, they've shared some factors. But what happens when they don't have any factors in common? Like these four objects, they don't have anything in common. In this case, we're going to have to figure out the least common denominator of both of the expressions. And by doing that, in order to do that, we have to find out the product. So for example, look at this one. 3y over 2y minus 1 minus 4 divided by y minus 5. So there is no common factor between these two. So we have to create our own by just simply multiplying these two. And I'll show you how to do this within the example.
All right, so here we have this example from the slides. I just wrote it down, and we figured out that the LCM will be the product of these two denominators, right? 2y minus 1 times y minus 5. So from here, we go on what we did before. So we're going to have to get this denominator for both of these expressions. So in order to do that, how would we do that for this one? Well, all we'd have to do is multiply it by y minus 5, right? To get this denominator, to get 2y minus 1 times y minus 5. And then what would we have to do for this one? It's the same thing, y minus 5. We'd have to multiply by 2y minus 1 because y minus 5 is already part of the denominator on this expression. Okay, so, and remember, if we're going to multiply something on the denominator, we also have to multiply it on the numerator. So that's exactly what we're going to do here, 2y minus 1. So we said we're going to multiply by y minus 5. So what we're going to do here. So y minus 5 by y minus 5. Okay? So we get 3y minus 5 divided by 2y 1 times y minus 5. There we go. Okay. And then we're going to do the same thing for 4 over y minus 5. We're going to multiply by 2y minus 1. 2y minus 1. You're going to get 2 minus 1 divided by y minus 5 2y minus 1. Okay? And now, since the problem is subtracting, they have like denominators, and we just subtract them like normal fractions. So you would get 3y 5 minus 4 times 2y minus 1 over, since they're like denominators, I'm just going to put them under the same denominator. And we can simplify this furthermore by distributing, right? 3y squared minus 15y minus 8y plus 4 over 2y minus 1 times y minus 5. Okay, and then it looks like we can do 3y squared minus 23y plus 4. And then we get that over 2y minus 1 times y minus 5. Okay, and that would be our final answer because we can't really simplify anymore. So that's just going to be our final answer. And bam. So you can see the most important part of this is that if you don't have these common factors within these two expressions, you're just going to have to multiply them to get the least common multiple. and then do the same steps we did when there are common factors. So just multiply the numerator and the denominator by whatever you need to get this denominator. Okay, and if I added, it would be the same process. This would just be a plus symbol instead of a minus symbol. So addition and subtraction, they follow the same rule and they're going to operate the same way. So let's move on to the last scenario.
All right, now the final scenario. When you're adding and subtracting more than two rational expressions. We actually did this on a slide before, where we added three different fractions. We had to find the least common multiple of all three of these fractions. And in this case, it's 40, so we multiply 8 times 5, so we have to multiply 5 on the top as well. Here we multiply 8. 8 times 4 is 32. And here we multiply by 4, so it's 28. And you get the answer 85 over 40. So when you're doing rational expressions, it's the same principle. You just have to find the least common denominator or least common multiple of the three denominators and then apply it to every single fraction or every single expression. So I'll show you how to do this with the last example. And it's the same thing with subtracting.
All right, so here's the last example. And like I showed in the slides, it's going to be three different rational expressions. And we're going to have to do the same thing. We're going to have to figure out what the LCM of these three are going to be. So let's do that right now. So 3y would be 3 times y, okay? And then x is just x. You can't factor that out anymore. And then 9 is going to be 3 times 3. So the least common multiple of these three denominators is going to be 3 times x times y, which is 9xy. So we're going to need all three of these denominators to have the same denominator, that's 9x y. Okay? So how are we going to convert 3y to 9xy? Well, we're going to have to multiply x, right? So we're going to have to multiply x to get it to 3xy, but then we also have to multiply 3. So in total, we're going to have to multiply 3x, okay? Now for x, in order to get it to 9xy, you're just going to have to multiply 9y, okay? And then for 9, you're just going to have to multiply xy. Okay, so these are the things that we have to multiply them by. So let's do that to the numerator, to their corresponding numerator as well. So if we go over here, we have y squared over 3y, and we said we're going to multiply it by 3x, right? So let's just do that. 3x to the top, 3x to the bottom, okay? And you get 3xy squared over 9xy, right? Because that's our least common multiple, 9xy, okay? And then you have 2 over x, same thing, where you said we're going to multiply 9y. So let's go ahead and do that. 9y to the numerator, 9y to the denominator, and you get 18y over 9xy, okay? And then you get 15 over 9, and then xy over xy, 15xy, and then you get 9xy, okay? So now we have every single one of these terms in the same denominator. And like I've continuously said, now it's just normal subtracting with like denominators. So we get 3xy squared minus, because this is minus, right? So minus 18y minus 15xy over 9xy. So this would be the answer, but if you want to simplify it furthermore, you could take out 3 from the top, and you would get xy, right? Because 3xy squared. and then you would get 6, and you would get 5x. Okay? And then on the bottom, it would still be 9xy. And now you can cancel out the 3, right? Because you can factor out the 3. That would be 1. Divide by both by 3. 1, and then 9 divided by 3 is 3. Okay? And then you can also factor out the y as well, because you can divide the y from the numerator and the denominator. That gives you 1. So you're left with xy minus 6 minus 5x over 3x. And that would be your simplified version of the answer. That would be your final answer. So it's essentially the same thing, but you're just going to have to, with 3 or 4, you could even have a positive, like 18x over 2x. You're just going to have to find the least common multiple of that that works with every single one of these expressions. So it's just a matter of that, and then once you find that, everything else is pretty much the same. So that's just a little small thing that you have to recognize. But essentially, that's pretty much it.
Well, that's it. So here's a brief summary. So for multiplication of rational expressions, it's the same thing as numeric fractions. There's two methods. You can either multiply and then factor, or you can either factor and then multiply. But when you're dealing with quadratic expressions or multi-term polynomials, it's easier to factor and then multiply. For division, you're just simply finding the reciprocal and then following the same steps of multiplication. For adding and subtracting, to add and subtract rational expressions that share common factors, you're going to do prime factorization of each denominator, and then you're find the least common multiple. And if you have no common factors, the least common multiple is simply the product of the two denominators or three denominators. And it's essentially the same thing. Once you find that same denominators, once you make every fraction have the same denominators, you're just adding and subtracting like you would regular fractions. So that's pretty much it. That's all there is to performing operations with rational expressions. So hopefully this video helped you get a better understanding of doing rational expressions with operations. And thank you for watching.